My name is Brendan, and about a week ago, a colleague came up to me, Matt. He's a developer, he's not a kernel engineer, and he said he had a performance problem. His application was leaking file descriptors, and it kept growing and growing and growing. And he wanted some information on how the application was leaking file descriptors, and he guessed that BPF may be able to help. So I'll start with a quick demo. All right. Now, I had not done this before using BPF or BCC, but I was interested in tracing the kernel function that allocated a file descriptor because that would give us a starting point for analysis. Since I hadn't done it before, I started looking around in proc KLSIMs, which is all the kernel symbols to anything containing alloc, anything containing both alloc and FD. And so I found a few. So FD alloc, map alloc, alloc FD mem. These are all kernel functions. And if you're looking at them thinking, I have no idea what any of those are, you're not alone. When I look at these, I don't know what many of them are anyway, because there are tens of thousands of functions in the kernel. But by using a tracer, and especially with BPF, I can quickly find things of interest. So using a tool, I wrote, let's start by, I think it might be one of these functions, so alloc, underbar, alloc FD, or it might be alloc FD array, map alloc, one of these. I can start by counting them all and saying, are any of these firing on the system? I'll switch into another window and just do some workload. And while I was tracing, I found that the system ran alloc FD table once, alloc FD mem twice, and alloc FD, underbar, alloc FD 23 times. That sounds like a pretty good target point for me to begin my analysis. From there, I can then simply trace that function and then print out kernel and user stacks. And so it's a bit boring on this system, but there's my kernel stack and user stack every time we hit alloc FD. And the kernel stack lets me know if it is via an open or if it's via a socket. These are all file opens. The user level stacks for LS are broken at the moment, but for Matt's application, they are much more interesting. And so very quickly, I was able to use a one-liner and create observability and instrumentation that had not been done before on the system, and helped Matt with that issue. Has anyone seen Stranger Things, a Netflix original? Great, awesome. So without giving too much of it away, with Stranger Things there is a character in it, her name is 11, and she has superpowers. And it's interesting through the show as she's not quite sure what superpowers she has and is learning and discovering them and discovering how to use them. And I feel that BPF is at a very similar stage. We now have these awesome capabilities that we can use in production systems, and we're using them on production systems at Netflix. But we don't know everything that we can do with them yet. And so it is as though we are discovering superpowers. The engineer that created eBPF, and he began work on it, Alexei Stoytoyev, a few years ago, in his early descriptions of eBPF, which was merged into the Linux kernel, he listed the different things he thought it could do. And one of them was simply crazy stuff. As a kernel engineer, you don't want to say crazy stuff when you're asking Linus Torvalds to accept your patch set into the kernel. But somehow it did get integrated, and it has allowed us to do crazy stuff safely and in production. A tool that I keep mentioning, so these tools use BPF as a backend for driving programmatic tracing. A tool I keep mentioning that seems to be quite popular, and this is another example of where BPF can be useful. With BPF, it's great to create canned tools, whether they're CLI or at the GUI, that people can just run. So I don't expect people to navigate kernel source and random kernel functions to answer problems. There's a lot of canned tools that you can just run, like your toolkit of tools. And this one that keeps coming up is TCP Life. This was originally suggested by another engineer on Twitter. Julie Evans asked, I just want a tool that can say, who's connecting to port 8080? So who is using that port? And just trace it. That's a great idea. There should be a tool for that. And I developed TCP Life using BPF as a backend. Nice example in that if you look at this, you might think, well, I can do this using TCP dump, and I can get some of the information out of TCP dump. Well, you can certainly get the local address, local port, remote address, and remote port. This is showing the TCP sessions as they complete. You can't get the process ID and process name out of TCP dump. Those details aren't available. So that's something we can dig out of BPF. But something that excites me in particular as a performance engineer, if I wanted to understand this on production, I don't really want to run TCP dump and then log every packet. So we have systems of 10 gigabit Ethernet interfaces. They can do millions of packets a second, so there's quite a high overhead to instrument that. This tool that I wrote does not instrument send receive. And so all I'm instrumenting is the events that change a TCP state. Basically when you create a TCP session and then when it closes. And I can get the timestamps out. Fortunately, both Google and Facebook to the kernel have added these counters that show us the throughput, transmit and received. And I can dig out lots and lots more information. I can dig out buffer sizes and how often we've retransmitted. Anything you see from netstat -s, I can associate it with a session. And so I've had many other teams at Netflix look at this and think, oh, we need to be running this. So our security team wants to run this all the time so that they can see who's connecting to who within the Netflix environment. Our network engineering team are also looking at deploying this as well. But it's just a nice example of, now that we have superpowers and we can instrument everything, you can design the tool that you want, and you're not bound by what the system gives you. That's one tool out of many. There is an open source collection of tools called BCC, and I've decorated a diagram of the operating system with many of the tools that exist so far. And I've been creating tools as we encounter issues and we need to be able to solve something. The most important thing about BPF when it comes to Linux tracing is that it is in Linux. There have been other Linux tracers before, and there's been great work in Linux tracing, but actually getting it integrated into the kernel has been a big challenge. You want your code to be integrated into the kernel, as then all the other maintainers help improve the performance, help reliability, help security, and enhanced BPF landed. So in some ways, it won the tracing war and is now what many of the front-end tracers will be using as a back-end. So I'll explain exactly what BPF is and the BCC tools. I'll go through some CLI tools and visualizations. The takeaways for you is to identify possibilities of Linux tracing superpowers, to hopefully upgrade to Linux 4.4 or 4.9 is better. Hands up if you're on at least Linux 4.4, if you know that. Oh, that's pretty good. I probably have half the people. Hands up if you're on 4.8 or 4.9 on your, okay, fewer people. So we are running some 4.8 at Netflix, which is great, because I get to use many more of my tools. But 4.4 has many of them, just not all of them yet. And also takeaway is to ask for eBPF support in whatever performance analysis or monitoring tools you have. And so Matt, who asked me to work on his file descriptor problem, he didn't need to know how to use BPF or understand the kernel at all. He just needed to know that it was possible. And so then he could ask someone to do that. And I think that's a big takeaway for everyone, is not so much needing to know how to write these tools or how to drill into the kernel yourself, but knowing that it's possible so that you can ask someone else, you can get help, and answer those questions. I work at Netflix. It's an awesome place to work. We're deployed on Amazon, Linux, Ubuntu for the cloud. We have a CDN that's based on FreeBSD. And to really illustrate that a bit more, eBPF is this superpower that lets you see anything inside the system. But who at Netflix exactly is going to use this? And so I think many people at Netflix has thousands of engineers, many hundreds of engineers will be using BPF as we keep adding it to our self-service GUIs. So that you can, we have different GUIs for analyzing a system. One of them is called Vector for per instance analysis. which is what I've been working on heavily for the last few weeks. And an engineer can bring that up, they get a dashboard, they can click a button, and they can get eBPF-based reports to understand performance in very deep detail. And I think that's what a lot of people will be doing with BPF. There will be fewer people at Netflix who actually SSH onto an instance and run the command line tools. They're great to show that things are possible, but most people, I think, are going to ultimately use them through GUIs and wizards. Hands up if you SSH onto your instances regularly. How many people do that? Okay, so still got a lot of people. That's not bad. So we have a chance to use these tools. I know with the cloud, we're moving away from that wherever possible. So I think at Netflix, maybe there'll be a few dozen engineers who will SSH onto instances and use the tools. We're shipping the BCC tools on all of our instances. It's part of our BCMI. And then when it comes to who at Netflix will write the tools, and we'll actually learn this in detail so they can create new ones, currently that's probably only about 6 engineers of the company. And so we've got a couple of people on the performance and operating systems team who can do it. We've got a couple of people on the network engineering team, and a couple of people on the security team. But most people need to know that it's possible, so they know who to ask, so they can get things done. So BPF itself. BPF is this arcane technology. It stands for Berkeley Packet Filter. If you run TCP dump and then give it an expression, so match this host and this port, and then give it -D, it will print out this instruction set, assembly. That's BPF. TCP dump has been optimized decades ago in the 80s by having a optimal virtual machine running in the kernel that will execute these instructions efficiently to match your expression. If you had this idea that TCP dump is dumping everything to user level and then filtering there, it hasn't done that for a long time. It's been optimized. Well, this is just a weird technology. Great. So there's this in-kernel virtual machine that has its own instruction set, and it's used by TCP dump. eBPF enhances that virtual machine. And this was developed by Alexei Storytoyev and others. The initial use case for eBPF was, instead of just filtering packets, which is what TCP dump does, what if we could programmatically redirect packets? If we could create an in-kernel software-defined network so that we can do NATing, create a virtual routing, whatever we need. And that's where Alexei started work, but he kept adding enhancements so we could do more and more things. And it's ended up being this sandboxed virtual machine in the kernel that you can write user-level programs and have the kernel execute. I've drawn a diagram of the internals, and this is how we're using it for tracing. But of course, eBPF can be used for software-defined networking, DDoS mitigation, a number of companies are using it already, intrusion detection, container security. So with BPF, it will attach a program on an event. And that event might be a trace point. Trace points are static locations in the kernel, like doing a disk I/O or doing a kernel context switch. Dynamic tracing is where there's K-probes and U-probes, those are the backends. This is where we can instrument any software function, and then we can run our own event based on it. Like when I was tracing FD-alloc, or alloc-FD, and then looking at the stack backtrace, I can do a lot more if I wanted to. And then there's perf events, so I can do sampling, I can do performance monitoring counters for the low-level CPU events. So there's all these event sources, and we can define our own user-level program that will get compiled into BPF bytecode and sent to the kernel and then executed on these events. It's great for performance engineers like myself, as I can develop observability tools that can do in-kernel summarizations and do all sorts of great things, like TCP life and so on. The way the kernel will share data to user level has been optimized, which helps make this production safe. And so there is asynchronous copies of either per event data, and there's also this idea of maps, where we have an associative array where we can store anything we'd like, and then user level can read that at whatever interval it likes. So that's used for summarization, doing histograms, doing frequency counts. And just to make clear how different this can be for non-BPF type or non-tracing type tools, if I wanted to look at TCP retransmits, the old way may be to use TCP dump, trace the send-receive path. Now that has some optimizations, TCP dump has, and there's ring buffers as well, but I still ultimately need to take all of those packet events and do something with them to post-process them and identify that there has been retransmits. So in my diagram, I illustrated that with there's all this data we have to send to TCP dump. That might be dumping it to the file system, that then dumps it to disks, then I have to post-process it and identify the retransmits. Whereas in the new world, if I'm using traces in Linux, I put my finger on the kernel function that does the retransmit, TCP retransmit SKB, and I just trace that. And then I summarize those details and can send it to user level. And by only tracing TCP retransmit SKB, I'm not touching the send-receive path. So I can do this basically almost for free in production, as it's a low-frequency event. Now, this is why I said Linux 4.9 was exciting, but Linux 4.4 is not too bad. We can attach BPF programs to many different event sources in the kernel. And so I already mentioned uprobes and kprobes. That's for user level and kernel level dynamic tracing. There's PMCs for hardware level events, and so on. I'll share these slides after the talk. They'll be on the Velocity website as well. If you've been keeping score with what's happening in the world of Linux tracing, eBPF is fairly new. And it's only been developed for the last 3 years, but it's one that has been integrated. And it does make use of many prior technologies that have been integrated over the years. Now, coding in eBPF is really hard because eBPF itself is that instruction set. We prefer to have front ends to it. And a front end that, the main front end that everyone's working on is BCC, the BPF compiler collection. It provides either Python or Lua. I think there's a C++ front end someone just merged into, so that you can write programs and then use BPF. And we can add more front ends as well. BCC also is the repository for where we've been sharing tools. So my TCP Live tool and many others, they're part of the BCC collection. It's on GitHub. I don't expect many people to write BCC BPF. If you want to, that's great. But just to give you an idea of what it looks like, this program has some C code that's in the quoted strings, and that runs in kernel context, and then has some Python code for formatting it and printing it out. So that's an example BCC BPF program. They're fairly short. I think a lot of people will take the toolkit and use it, or if they have access to a GUI that has BPF-based agents, they'll use that as well. But it might be helpful to know that the BCC BPF programs, they're not that long, and if you needed to customize them, that should be doable. Some people are trying to make it much simpler. And so here's an example, ply, and that makes the front end trivial. So you can do one-liners. That's doing a power of 2 histogram of the read system call size. So the tracing landscape as of now, I would say looks like this. Many of these traces are not part of the Linux kernel. The ones that are really interesting are the ones that are integrated, which includes ftrace, perf, and BPF. And so BCC and BPF has great capabilities. It does not have great ease of use. It's, like I said, a little bit tricky to write those programs at the moment. That's where something like ply can help, although ply is still being developed. Now, BCC BPF tools at the command line I'm a pragmatist, and I don't think the first stop for any performance issues should be advanced tracing tools. And when my colleague Matt was working on the file descriptor issue, we were already using LSOF, right? because LSOF can give a lot of information on file descriptor growth. And just to help people get their head around that, I've included a checklist I published a couple of years ago. This is my Linux performance analysis in 60 seconds. And I generally will do this before any performance issue if I'm SSH'd onto a machine. At Netflix, we try to make everything automated through self-service GUIs. So something's wrong if I actually have to SSH onto an instance, but if I do, I'll go through these commands. And they solve a lot of the low-hanging fruit. Using tracing tools is where I can drill down deeper and go more advanced. Installing the BCC toolkit at the moment is pretty simple. It's adding a repository, apt-get install BCC tools. There's instructions online for Fedora and other operating systems as well. Canonical have also published an Ubuntu Snap, which also makes it very simple. When you install it, you will end up with lots and lots of tools, all of these tools. So to help navigate these, I've also created another checklist. This is the top 12 tools I might use out of the however many we're up to now, 60, 70 tools. So exec-snoop, OpenSnoop, ext4slower. Many of these are workload characterization tools, so they give you insights into what the system and kernel is doing. So just to run a few. So I've got my, oh, not that one. So exec-snoop I've actually written exec-snoop in many different traces before. This is just my latest version of exec-snoop. If I SSH back onto this instance, it will tell me these are all the commands that will run just to allow my SSH to complete logging in. You can see how it's running all this update MOTD things and failing. So it's getting a -2. I think it's walking the dollar path variable. Great for workload characterization. OpenSnoop will show what files are being opened. So easy local time. But there are many of these tools which I'll go through. They're very easy to use. They also generally have a usage message. So you can, maybe I want to match on a particular process ID or include timestamps with the column and so on. I just remembered, I changed my message of the day when you log in to be Commodore 64 style. So, all right. So exec-snoop, that's for discovering short-lived process issues. And I've seen this many, many times. Top does not show you short-lived processes. If you do a build and you run top, you'll see you've got a high load average, but you won't see the processes. If you run atop, you'll see them because atop does use process event tracing. Exec-snoop is a nice way just to dump them all that are happening. And when people, especially when people are micro-benchmarking on the Netflix cloud, I get them to run exec-snoop first, because sometimes there can be runaway scripts. So something's misconfigured and it's in a loop where it's sleeping for 10 seconds and trying to run commands. And that will create perturbations if you're trying to do some sensitive micro-benchmarking. So yes, I get people to run this, and we do find things all the time. This output that I included in the screenshot, just as I was updating these slides, I realized I caught something weird. This is from a production machine, and I can see it's looking for bash under /command bash. That's not where bash lives. Then it's looking under user local bash, user local sbin bash, and then bin bash. I think I could get a performance optimization just by changing the path variable on our Netflix instances for whatever this is. It's actually doing it pretty frequently. This is in a loop, and so that was doing it every 20 milliseconds. It was doing these lookups that don't exist. Another favorite tool of mine is ext4slower, and I have versions of this for XFS, Btrfs, and ZFS, and I can basically write it for any file system. With ext4slower, you give it an argument, 1 for 1 millisecond, and it will show you file system I/O that's slower than 1 millisecond. So what's interesting here for this output is we had one slow I/O, which was a type S for synchronous, so a synchronous I/O to system.journal. And if you look at the timestamp column, you'll see this spanned a period of 4 minutes, and we only had one slow I/O. If an application developer was telling me, I have a disk I/O issue on this instance, disks are so slow, I could look at this output and say, well, I don't think that's true. I think I just exonerated the instance. You only had one slow I/O in 4 minutes. That's a pretty gentle rate. If that was happening every 100 milliseconds, you were getting slow I/O, I could understand why they would start to hurt percentiles. But this is a great way to exonerate the storage subsystem. And using the tracing tools, I can measure at the top of the file system when the application talks to the file system instead of down at the disks, because this is what the latency that the application actually suffers. The application doesn't wait on, well, the kernel tries very hard so that your application does not wait on the disk. So that's doing write buffering, doing read ahead, all these ways so that your application is just bouncing out of DRAM cache, and then sometime later the disks rattle. So that's why looking at the I/O to the file system is more important if you want to understand why the application is slow, or if it's slow, due to the file system or disks. Looking at the disk performance is interesting for a different reason. That's workload characterizing what the disks are up to. I collected this output from this morning, actually, on our production container instance. So good to see that things are behaving well. Looking at the disk performance, there's another tool in BCC that will summarize disk I/O latency as a histogram. And so that's biolatency. And the options I've used here, milliseconds and print a timestamp. Every 10 seconds we'll do the summary. And so this is printing an ASCII-style distribution. And that's great for also exonerating or understanding more about what the disks are up to. I see too many performance analysis GUIs that are plotting average disk I/O latency. Average latency? And they're getting this from the same place that IOStat gets it from. They're getting it from the kernel disk stats. Average latency can be very misleading. Disks have onboard cache, and so some events can return very quickly, and then some can be slow. And so you'd want to know that there's two modes of latency for your disk requests. What's interesting here for this output, which I gathered only a few hours ago, I'm more looking for outliers. So 27 I/O during that 10-second period, we're in the 128 to 255 millisecond range. That's pretty high. That's high. And lots of them were much faster. Lots of them were slower than 16 milliseconds. Although 16 milliseconds is still pretty slow for disk I/O these days. That sounds like either rotational disk I/O latency, which is not, or it's queuing, which it is. And so in this case, the kernel has queued a lot of I/O at the same time, and so some I/O are waiting their turn in a queue, and so you end up with longer latency. And of course, I can instrument that in more detail if I need to understand. TCP sessions, I mentioned this earlier, TCP Life, which is a favorite tool of mine. It's becoming the favorite tool of many other people. And that's where we can pull out statistics like the process ID and command, and also the duration. And thank goodness that there are kernel counters for the transmit and receive bytes, so that I can just put it all together and print it out. The network engineering team at Netflix has been looking at this very, very closely and are excited by how much more stuff we can add. So they can take the source code to this and keep adding columns and print out anything inside the kernel if it's interesting for production triage. DNS issues, because it's always DNS. This tool, instead of using kernel dynamic tracing, it's using user-level dynamic tracing of the get attr info and get host by name functions. This is great, as I can walk up to a machine and say, resolve these user-level functions, instrument them for whatever processes are running. And then now I'm instantly getting latency information. And so I know of one company that's already automated this so that they can log slow DNS latency and get alerts very quickly, which is pretty cool. And so here, if I was looking at this, I'd say, it seems to span a while, so this system is not making that many DNS requests. We did have one that was 52 milliseconds, though, which sounds like it's a little bit slow. Another example, run qlat. I was asked, I always write, for whatever operating system I work on, I always write one of these tools because I like to I like to understand what the scheduler is doing. And so here's my latest incantation for Linux. This is run qlat. And I was asked late last year about, there was these posts going around where people claimed that the Linux scheduler had some fundamental issues and had high latency. And so some engineers at Netflix were worried about, do we have hidden latency issues? Is the scheduler making the wrong decision and leaving threads running on a CPU when it should have migrated the threads? And so I was able to use runq latency and some other BCC tools to prove that our scheduling on our system is fine. We have very low latency. And that's pretty low. So that column is microseconds. And out of the over 100,000 events there, I only had 5 in the 4 to 8 millisecond range. So runq latency is when your application becomes runnable, but it has to wait its turn. And so it's a really interesting performance metric. Now, those are some canned tools, but it's important to understand that you can also do advanced analysis. And to explain a little bit about the methodology I use, I will find or draw a functional diagram. So I've got a functional diagram on the right. This is just a random functional diagram of a storage I/O subsystem. And then I'll apply performance methodologies. What's the workload characterization to each functional block? What's the latency to each functional block? There's also my use method for utilization, saturation, and errors, and I can try that for each functional block. By performing those methodologies, you're starting with the questions that actually matter. This is the biggest difficulty with eBPF and with system traces in general. They're amazing. They can instrument thousands of things. I can instrument any kernel function, any user-level application function. What do I do with that? And this is like 11 trying to figure out what superpowers do I have and how can they be useful. By following the performance methodologies, it helps you realize what you can do with it. So it helps you find the questions you then want answered of the system. And it's different because before these tracing tools existed, and I was doing performance engineering, we would get the vendor manuals for the operating system, and then we would study the tools that the vendors gave us, and that's it. And if there were blind spots, we became really good at reading the tea leaves and inferring what the kernel might be doing without any means to instrument it. But nowadays, if we want to know what the kernel's doing, we just measure it. If I want to know what the resolver library is doing for DNS lookups, I can just instrument it. So it's a different way of thinking. There are some multi-tools in BCC I want to mention as well. And you can construct some fairly powerful one-liners with trace. Trace was developed by Sasha Goldstein. Was anyone in Sasha's BPF tutorial 2 days ago at Velocity? So a number of people. This is a great one-liner. It's fairly powerful. You can do much more complicated things. That was looking at reads bigger than 20 kilobytes. And another tool of his is argdist. And so that example is I'm taking a kernel function, TCP cleanup, rbuff, and I'm saying, show me the copied argument. This actually reminds me, about a month ago, is another example of using this at Netflix. We had a patch set to one of our runtimes that changed the socket size being used. And this is going to be a fairly significant change for Netflix to incorporate this patch set. And the engineer was saying, this helps really a lot, it will improve your performance, you need to include this in your runtime. And I looked at the patch set, and the patch set changed the socket maximum buffer size from 128 kilobytes to 16 megabytes. And we're thinking about deployment, we're going to have to build our own patched version of the runtime and then deploy it on tens of thousands of instances. And I thought, no, hang on, I'll use argdist and I'll find out what our in-use socket maximum buffer size is. And I found out it was 12 megabytes. It's like, well, that's actually not the default of 128K, so I don't think we're going to get a huge performance win. And then later on found that some engineer years and years ago had already tuned this. And so I was able to save a lot of work at Netflix just by, instead of thinking, this tunable parameter must help, like let's deploy it everywhere, just getting some data first, and then realizing that it had already been tuned. Visualizations. So I went through many CLI tools, and they're great for demonstrating the capabilities of BPF, but not many people are going to be SSHing on. If you do, that's great. At Netflix especially, people will be using our vector self-service UI and other UIs to get BPF metrics, where you can click a button and you get flame graphs and heat maps and tracing reports. And I spent the last 3 weeks working on this intensely on Vector. Visualizations that make sense include heat maps. So this is a latency heat map, and these can be drawn in different directions. This one's BPF-based. It's actually part of the Linux kernel. And on the x-axis is showing latency, and on the y-axis is the passage of time. And the cloud that you see shows where the I/O latency was. So most of the time, our I/O latency is about 10 milliseconds. But about halfway through, we start to get some faster I/O latency. So this is a great way for finding out not just the average I/O latency that people plot, but the distribution. So you can look for multimodal distributions and outliers, and also time variance. So you get to answer lots of things at once. Anyone using flame graphs? Okay, so we've got at least a couple dozen people. That's great. Flame graphs, we get to use them more with BPF in that there's many types of flame graphs that were impractical before. So off-CPU flame graphs involve flame graphs are a visualization for stack traces. If you haven't used them, they're great. They're very simple. It's a simple Perl program. And actually, there's more than one implementation. You can implement it yourself in probably a couple of days if you were inclined. And it just visualizes the stack trace so you can navigate and understand where your code is spending its CPU time. But there's a different type of that for off-CPU time, so I can see why my code is blocked. And BPF makes this possible because it's so efficient. I can summarize that information in kernel. And once I'm looking at blocked paths, I can then attack many types of performance issues. I can look at resource I/O, lock acquiring, sleeping, and so on. A really advanced one is this off-CPU flame graph I came up with, which is showing the blocked stack. But in the kernel, I'm using BPF to associate the waker stack with it, so that I can see not only this is the stack trace that blocked, but this is the stack trace that woke it up. And so often that's important for understanding why we blocked. Future work, adoption is a big challenge for BPF. And I think what will help is getting this integrated into performance monitoring and analysis products. And then other non-technical things like marketing, documentation, training, community, they're very important as well to get people to understand and use BPF. A higher level language will help. And some people are trying, there's a project called Ply, which is on GitHub, and it looks like this. So you can do some powerful one-liners with Ply. In fact, you can do really powerful one-liners. This one is measuring read latency as a histogram, and that's 2 or 3 lines. That's still in development though, so some way before we'll be running that in production. So that's a quick rundown on BPF, and the takeaways I'd like you to have is not so much how you can write these tools, or even all the different tools that exist. These diagrams are online, there's many, but understanding that it's possible in the first place. So like the engineer, Matt, who came to me and said, he knew I was doing BPF, and he said, I think you can help me with my FD alloc issue. And so I was able to spin up a one-liner. In fact, if my one-liner didn't work for him, I was going to write a much more complicated tool that would save away stack traces on file descriptor allocate and a timestamp. And then later on, when they were freed, I'd delete the stack trace. But I'd poll it every minute to see if there are any long-term survivors, which would really identify leaks. But I didn't need to. He solved the issue quickly. But that's the thing I'd like everyone to have as a takeaway, is knowing that you can answer virtually any question inside of the system using these new tools, and also to upgrade to a new version of BPF so that you can use them. In the slides, which I will share, I've got links and references, including a BCC tutorial that I wrote, in case you'd like to program this yourself. Thank you very much.
We'll take a couple of minutes for questions. Hello. Good talk, thank you. My question is, it looks like in a lot of those cases, you sort of talked a bit about visualization, a bit about companies beginning to do some analysis over constantly collecting data. Do you see that? How do you see that sort of progressing and moving forward? Because immediately when I saw you sort of pointing out a couple situations, like, oh, like let's collect all this data constantly and I don't know, do analysis and alerting on it. And so I'm curious, like, where do you think this is going?
So with BPF, I think it is, for the question, will we see monitoring tools that have this, say, enabled 24/7, would be one part of answering that. And I think we will, but where this is great for performance analysis monitoring products is to, if I'm working on one, I'm trying to sell to my customers and I find out there's some needs to help the customer, I can prototype it quickly with eBPF. I can run it on the customer production systems. And so they are effectively using eBPF 24/7 using this custom tracing. And then later on, I can make the case to change the kernel or the applications so that that is baked and built in. BPF can be a great prototyping tool for performance monitoring companies to say, it makes sense if the kernel could only provide these 10 metrics. So you just roll them yourself in eBPF, you run it, you prove it with some customer data, and then you end up doing a patch set. So in that scenario, eBPF is really a transitional solution so that you can, because you can always deploy eBPF, you can write a new tool and deploy it on a customer production system without even restarting the system, right? It's like, oh, they need this. I write it, I copy it, I run it, done. Like, don't have to restart a single thing. That's great, but in the long term, you might think, you know, it's more efficient if there was just a bean counter in this kernel struct. And so I think it should see a role of prototyping and proving the addition of new kernel instrumentation. So some of these tools that I wrote, in 5 years from now, the tools may exist, but they may not use BPF. They may use like some proc, like it may be in proc now, or maybe some other way. If not, for really custom and one-off stuff, it's probably going to stay eBPF forever.
I think we have time for one more question.
How dangerous is my attempt to write any of the eBPF like C++ kind of code? Like, can I do something bad to the system with that? Can I hang it up? I don't know.
So eBPF runs in a sandboxed environment, and every read and write to the system goes through this single gatekeeper function, BPF probe read, and there's a write gatekeeper as well. And when in the BPF program, you can only read and write, manipulate things on a very tightly controlled BPF stack. It can be a pain at times, but it's designed that way so that it's sandboxed. The only thing you can do, you should be able to do to negatively interfere with your system is trace too much. And if I were to trace scheduler events, which are very frequent, it's actually not that bad, but if I was to dump them all to the file system, now I'm doing disk I/O, I'm doing file system CPU, and so that's why I try and summarize things as much as possible. So the thing that worries me the most about eBPF is not crashing the system or crashing applications, it is the cost of overhead. And it's pretty easy to test. If you had a workload, you turn on the eBPF program, you turn it off, you have a look at how much performance degraded, and so you can quantify it that way.
Thank you again, Brendan.
Thanks.